Hello again, physics friends. It's good to see you again, and we have a really exciting topic for today. We are going to talk about something called the space-time interval. One of the great and perhaps little known aspects of relativity for first-time learners is that not everything is quote-unquote relative. There actually are certain quantities that are the same in all frames and the same for all observers. And if you think for a couple minutes, you probably can recognize one of them, namely something that doesn't change and is always the same in all frames, the speed of light, right? The second postulate of relativity tells us that all photons travel at the same speed, independent of their frame of reference and independent of the speed of the source. So you might be wondering, as Einstein was, are there other quantities that all observers can agree on? What we're going to learn about today is a space-time interval. We'll define what that means in a moment, but we're going to learn that the so-called space-time interval is, in fact, a quantity that all observers agree on the value of. No matter what your frame of reference is, you might disagree on how you label space and how you label time, but a certain combination of space intervals and time intervals combine to form a space-time interval that all observers agree on. To bring this into life, we're going to focus on a specific example, right? And if you think back to a worksheet that we did last week, you might remember this problem where Alice is heading to the grocery store located 1,200 feet from her home, and we're told something about her speed and so on. We're going to use this specific example as our springboard here, and we're going to, rather than re-solve this whole problem, we'll just use the main results and then use those results to understand the space-time interval, okay? So I'm going to make this question a little bit smaller and put it on the side so we have it for reference. The basic idea is the following. We have a diagram here showing in the ground frame, there's a home and a grocery store, and Alice is flying from home towards the grocery store at 4/5 c. The grocery store is 1,200 feet away, and what we find is if you're moving at 4/5 c and you have to travel 1,200 feet, then that will take 1,500 nanoseconds, okay? So if we have, let's define two events. The first event is Alice departs her home, and the second is that Alice arrives at the grocery store. Well, we can ask in the ground frame, what is the space interval between these events? Okay, so the distance between the events and we'll do it in this ground frame, right? So if we draw a kind of a line dividing our analysis in the ground frame for our analysis in Alice's frame, the distance between the events in the ground frame is this distance. The first event happens at this location. The second event happens at this location. So that distance between events is 1,200 feet. Okay, so we can call that, let's say, delta x in the ground frame will be the separation between events. And we said that's 1,200 feet. And in fact, let me color code this a little bit. I'll use purple for this. So event 1 is happening at that location, event 2 is happening at that location, and those two events are 1,200 feet apart. And what is the time interval between these events? Well, we'll call that delta t, again, in the ground frame. And what is the time interval? Well, the first event happened at a time 0, and the second event happens at a time 1,500. So the difference is 1,500 minus 0, or 1,500 nanoseconds. Okay? Now, without much motivation or derivation, I'm going to define the space-time interval in the following way, and then we'll use it. We take the delta t that we just calculated, and we multiply it by the speed of light to get a quantity that has units of length, in this case feet. We square that quantity, okay, And from that, we subtract the separation between the events squared. So it kind of looks like a Pythagorean theorem type expression, although we have a minus sign instead of a plus sign. And so let's see how that plays out. So a space-time interval, in this case, is that would be 1,500 feet, because it's 1,500 nanoseconds times 1 foot per nanosecond is 1,500 feet. We subtract from that delta x squared, 1,200 feet squared. Sorry, both of these terms are squared. And when you do that, you find a number that's quite a large number. It is 810,000. Okay. Well, let's play the same game in Alice's frame. Okay. Where is the location of event 1? Well, that happens where Alice lines up with the house in this first diagram. So we have this dotted line represents the location of event 1. And event 1 is happening in Alice's frame at 0 seconds. Okay. Where is event 2? Well, event 2 is when Alice reaches the grocery store. That's happening right here also. So the distance between events in Alice's frame is 0. Both events in her frame are happening at the same place. They're happening at her, and she's not moving, right? Both events involve her. They happen where she is, and she's not moving. So there's no separation between the events. How about the time separation between the events? Well, the second event happens at 900 on her clock. The first one happened at 0 on her clock. So the difference is 900 minus 0, or 900 nanoseconds. Okay, if we compute the space-time interval, we have 900 nanoseconds times 1 foot per nanosecond is 900 feet squared minus 0 squared, and that ends up being 810,000. Exactly the same quantity that we found in the ground frame. So it turns out that this space-time interval is invariant. That's an exclamation mark, not a question mark. It is invariant, and invariant simply means the same in all frames. So a ground frame analysis would lead you to the calculation that the space-time interval is 810,000. And again, this is... Okay, so we have... Although Alice and the ground frame disagree on the distance between the events, and they disagree on the time interval between the events, or the elapsed time between the events, they somehow do agree on this quantity, the space-time interval. So why is that? How can that be? Well, to get some intuition for the meaning of the space-time interval and why it is an invariant quantity across frames, we're going to take a step back from relativity and just look at a pure space diagram and think about how we label the coordinates of points in a diagram according to the axes. So we're going to look at a point in space labeled with xy coordinates, and then we're going to rotate our coordinate system and look at the coordinates of that point in the rotated system, and we'll find another invariant quantity in that more familiar scenario. In relativity, we're going to talk a lot about events and the coordinates of the events, and what we're going to see is that the coordinates of events depend on reference frame. In other words, the x, y, and z and time coordinates we assign to events can depend on your reference frame, but there are some quantities that do not change and are constant across all reference frames. In preparation for getting our mind in that place, I want to make an analogy to just geometric arguments. So what we're going to do is bring in a picture here that shows 2 points on a plane. We have an xy plane, so you can think of this as like the floor, the ground. And the red dot here represents where you live, say your home, and the blue dot represents where you work. And let's say this is a coordinate system labeled XY, but let's be even more specific. Let's call it XA for Alice's reference frame and YA. So Alice in her mind is kind of setting up a grid on the ground, and she's assigning points on that grid. And her grid kind of runs east-west, let's say, and north-south. So X for her is east-west, and Y is north-south. And on that grid, she identifies the coordinates of this point, this blue point, and she would label them, Alice would label those coordinates as 4, 3 for an X coordinate of 4 and a Y coordinate of 3. So we actually can write this down. Let's say we'll say Alice, and then later we're going to introduce Bob. So I'm going to create a table here with Alice and Bob, and we're going to write down the coordinates that Alice assigns for each of these points. So Alice would say her home is at the origin, 0, 0, X, Y, and her work is at 4, 3, and these are units of kilometers, just to pick a specific case. Okay, so Alice has chosen to use east, west, and north, south as her coordinate system. But along comes Bob, who's a little bit contrarian, and he decides east, west, north, south is too straightforward. He wants to have a different coordinate system. So Bob chooses a different coordinate system. We're going to indicate that with a green line. And he actually chooses a coordinate system such that his x-axis goes right through the 2 points of interest. So we'll label this xb for Bob's x-axis, which is in kilometers. And we will label, we want another axis here. It's going to be perpendicular to the first, and that will be his y-coordinate system, or his y-coordinate, again in kilometers. So we'll label that y sub b for Bob's y-coordinate. And Bob then would disagree on the coordinates of these points, right? First of all, we can write down the coordinates for these 2 points, home and work. And for Bob, notice the red dot is still at his origin. So actually he will agree with Alice that home is at 0, 0. Work, however, he will disagree. He will say, no, it's not 4, 3, because the blue point is on his x-axis. And a point that's on his x-axis has a y-coordinate of 0. So Bob says the y-coordinate of his work is 0. Well, what is then the x-coordinate? Well, we have to do a little math to figure that out. But recall from geometry and Pythagorean theorem that you can have a triangle, and if the lengths of the 2 sides of that triangle are 3 and 4, then the hypotenuse will have a length of 5, a 3, 4, 5 triangle. And if you like, you can remember that the hypotenuse length is equal to the square root of the sum of the squares of the other 2 sides, in this case 3 and 4. So we'll have a square root of 9 plus 16, or the square root of 25, which is 5. So a 3, 4, 5 triangle means that the distance along one edge is 4, the other edge is 3, and this hypotenuse, which is the x-coordinate in Bob's frame of his work, will be labeled 5, because it's 5 units away from the origin. Okay, so he's now going to put this 5 in here for his coordinate. So Alice and Bob agree that home is at 0, 0, but they disagree on the label for work, right? Because the office for Alice is at 4, 3, but for Bob, it's at 5, 0. So you might think, okay, so this is an example where if you rotate a coordinate system, you change the labels of the points as described in those coordinate systems, okay? With the exception of the point that's at the location of the rotation, because that point hasn't moved relative to the reference frame, but the blue point has. So a perfectly reasonable question then is, well, is there anything that doesn't change? Is there anything that's conserved or constant? And I think your intuition will suggest yes, right? Like the distance that you have to drive from your home to your work should not depend at all on the coordinate system that you choose, right? Whether Alice or Bob describes the journey, they have to both agree that it's 5 miles or 5 kilometers of a drive from home to work, right? Whether you use Alice or Bob's frame of reference, you're going to use the same amount of gas on your trip. And we can be really explicit about that. We can write down the distance between home and work for Alice and the distance between home and work for Bob. In particular, for Alice, she would say that home and work are separated by 4 kilometers in x and 3 kilometers in y. So when I do the square root of 4 squared plus 3 squared, I find that work is 5 kilometers away from home. Bob also finds 5 kilometers, but for a different reason. He says, my work is 5 kilometers away in x and no kilometers away in y, but my work is still 5 kilometers away. So they agree on that quantity. Okay, and so what we can say here is that length or distance is conserved. If I could spell, that would help. Length is conserved when you rotate your coordinate system. So another way to say this is that we have an invariant quantity. Okay, and we can write this invariant quantity as delta x for Alice squared plus delta y for Alice squared is equal to delta x for Bob squared plus delta y for Bob squared. In other words, both Alice and Bob agree on the separation between points, even though they disagree on the labeling of the x and y coordinates for those points. Now, what we're going to see when we get deeper into special relativity is that length is no longer a conserved quantity when you change reference frames. We're going to see that the length of an object depends on the speed of that object in a given reference frame. Okay. However, what we're going to find is there are invariant quantities. There are quantities that all observers will agree on. It's just that in special relativity, that quantity does not just depend on distance. It depends on time intervals and length intervals. So we're going to introduce later an invariant quantity that all observers agree on, but that quantity will depend on x and time, t. So we just talked about coordinates, in that case, coordinates of objects in a two-dimensional space-only environment. Throughout relativity, we're going to make heavy use of this idea of an event. And an event is just something that happens at a specific instant in time at a single location in space. So some examples of events might be one photon emitted from a laser. Okay, that photon comes out of the laser at a single instant of time, and it happened at a single location in space. Another might be a photon arrives at a detector. Photon arrives at detector. Okay. How about the following? A photon travels across a room. Is that an event or not an event? Indeed, it's not an event, and it's not an event because traveling across a room implies much more than one instant of space and much more than one instant of time, right? This is a photon traveling across a room, spans the whole length of the room, and it takes some time for that to occur. Photon emitted on one side of a room is an event. Photon reaching the other side of the room is an event, but the whole journey is not a single event. Okay. How about, Physics 100 class on Wednesday? Is that an event or not an event? I would say not an event, right? Because first of all, the time of that class is about 75 minutes. So that's not an instant of time. And you could argue that the class takes place in an area that's the size of the classroom. Or, if we're remote, then it's kind of taking place across the planet. So we have a couple problems with that. Now you could say the start of Physics 100 class for a particular person, right? And that person would have a given location, and the class would start at a single instant of time. So that would be okay. So think about events. Just take a minute and think of a few events that actually qualify as an event in the lingo of special relativity. Any event or example that you came up with would have to satisfy this idea that an event can be labeled by a single set of 4 numbers, time, and then the location of the event. So we're going to think about events as coordinates in a space and time continuum. And for us, we're only going to consider one-dimensional problems. So the event simplifies to a time and an x coordinate because we're not going to think about y and z coordinates. Everything we'll do this semester with relativity will be one-dimensional, so it should be more straightforward. But everything that we talk about as an event has to occur at a single time and at a single location on the x-axis. In another video, we're going to talk about drawing diagrams to represent activities. So we're going to draw snapshot diagrams that represent the situation that we're studying. And each of those diagrams is going to represent a single instant of time. So it's a snapshot in time showing objects at different x coordinates, different positions. So anytime you draw a diagram that represents one of these problems, that's a snapshot in time. And so if you want to draw 2 different events that are happening at different times, you need a different diagram for each of those events. So in closing, in this video, we talked about coordinates and how different coordinate systems imply that objects or points in that space will be labeled with different numbers, even though distances between those points are conserved, at least for regular geometry. What we're going to see in the future is that in relativity, distance and length between objects is not conserved. That will depend on reference frame, but there will be a conserved quantity that involves both space and time coordinates such that that quantity is conserved and is the same for all observers. And in order to talk about that in more detail, we introduced this idea of an event, which was a single, an occurrence that happened at a single location at a single time. So we'll talk much more about that going forward.